In this video, we're going to look at constraint optimization from the point of view of Dixit's textbook, Chapter 3. And we did not deal with multiple constraints previously, but we're going to do that now. So we want to maximize a function f of x1 to xn, subject to constraints gi, where each gi is a function of x1 to xn, is equal to some constant, some number, ci. And the I are used to denote the different functions, the different constraints. And there are m constraints and n variables. So we avoid confusion with subscripts for derivatives by using the superscript here. So each of these superscripts, 1 through m, represents a different constraint. So we form the Lagrangian, as before, as a function of x1 to xn, lambda 1 to lambda m, and write it as the objective function plus the sum of all of these constraints. So what we have here, and here I break the rule where I just mentioned that we use that I in a superscript, we have alpha I, so these are our Lagrange multipliers, and there are m of them, ci minus gi. The first order conditions are the same as previously, and that is that the partial of L with respect to xj to any xj is equal to 0, and the partial of Lagrangian with respect to any lambda rather, is equal to 0. J goes from 1 to n, I from 1 to m, and m is less than n if we want to have a solution that's unique. So we solve the n plus m equations in the n plus m unknowns. Now we can write this same problem in more compact form as matrix vector notation, where we have L, a function of x and lambda, where x and lambda are vectors. Lambda is a vector, a row vector, 1 times m, and because there are m constraints, and x is a column vector of 1 to n variables to solve for. This piece in brackets is an m by 1 vector in the end, even though g of x itself is a matrix. The first order conditions we can write as partial of L with respect to x, and that's a function of x star lambda, where recall x star is our optimal solution, so that would be the solution, is equal to 0, and the same thing with the partial of L with respect to lambda is equal to 0. So this is written more compactly. Since g of x is an m by n matrix, so we got m of these constraints, and within each constraint we have the possibility of n variables. And as long as this m is less than n, then we want the rank of g of x to be equal to m to avoid a singularity. Because remember, the determinant of g of x would be 0 if this was not true. So then x star would be 0 as well. One further constraint requires that xj be greater than or equal to 0 to make economic sense of these variables. We can't very well have negative xj's because that would not make any sense. So in that case, some of the xj may be positive, greater than 0, while some are actually equal to 0. So when we solve this problem, the x is 0, and in most cases we'd expect it to be greater than 0. If the xj is greater than 0, then the partial derivative of the Lagrangian with respect to xj would be equal to 0. Okay? But if xj is equal to 0, then the Lagrangian, the partial of the Lagrangian with respect to xj would be less than or equal to 0, with the equality holding in rare cases. So for every j, we should have that the partial of L with respect to xj at the optimum is less than or equal to 0, and xj, the optimal solution of xj, is greater than or equal to 0. This is somewhat, Dixit uses the term with complementary slackness, but we'll expand on that a little later on. And this should hold as an equation. This result here should hold as an equation for at least one j. The requirement can be written more compactly as x star j times the partial of Lj with respect to xj being equal to 0. And this is really what we mean when we talk about with complementary slackness. And we'll expand upon that in the next lecture. Inequality constraints are the second thing we want to look at. So suppose the first constraint does not need to hold with equality. Rather, suppose we only cannot exceed the right-hand side of the constraint. For example, we may have a farmer who has 1,000 hectares of land and is busy planting it, but realizes they're short of labor, or they're short of something else, or maybe some of that land is just not worth bringing into production, and they end up maybe producing crops only on 800 or 900 hectares rather than the full amount. So we have some slack, some free land, if you like. And we can write that requirement as the first, with this referring to a 1, the first constraint is less than or equal to the right-hand side of that constraint. So in order to deal with this, we define a new variable, S1. And we use that S1 to refer to slack in the first constraint. So in that case, S1 is equal to C1 minus G1 of x. And S1 has to be non-negative. Then the new Lagrangian, and I use a little n there. I noticed that Dixit uses a hat on top of the L, is a function of x1 through xn plus this slack variable, and then it's a function of these lambdas. And it's equal to f of x, and we include the S1 in here. I think Dixit makes a mistake because he also includes these lambdas, but he can't, and he ignores the S1, but I think you have to keep it in there, even though its value might be 0 in the objective function. And we'll see that a little later on as well. Plus, and now we look at the first constraint. So we take lambda 1, multiply it by C1 minus G1x, so the left-hand side of that constraint function there, minus S1. And then we have the remaining constraints multiplied by this lambda j. So j now goes from from 2 to m because we've taken out the first constraint. And here we just have the regular constraints which we had before. So we can rewrite this as this Lagrangian, the new Lagrangian, as the old Lagrangian minus lambda 1 times S1. The first order conditions are the same as they had been before, but with one additional constraint with respect to, or one additional first order condition with respect to S1. And that is that the partial of that new Lagrangian with respect to S1 is equivalent to minus lambda 1, which is less than or equal to 0, while S1 itself is greater than or equal to 0, with this complementary slackness requirement that S1 times the partial of L with respect to S1 is equal to 0. And the next lectures will discuss these aspects in a lot more detail. Finally, we have what is called the Karush-Kuhn-Tucker theorem. And Dixit gives that on page 31, but he refers to it as a Kuhn-Tucker theorem. However, since he wrote that, they've discovered an MSc thesis written at the University of Chicago, which had predated the Kuhn-Tucker material, and this particular author of that master's thesis is given credit, and his last name was Karush, so we refer to the Karush-Kuhn-Tucker theorem. And we suppose that x is a row vector of n by 1, c is a vector m by 1. G is a matrix, m by n, and f turns out to be a scalar. And we define the Lagrangian as x as a function of x, and lambda is equal to f of x plus lambda times c minus g of x as normal, where lambda is a 1 by m vector. Now suppose that x star maximizes f of x, subject to this requirement that the constraints are less than or equal to the c vector, and that x is greater than or equal to 0, and that g of x has a maximum possible rank. In other words, it's non-singular. If it was singular, then the rank would be less than m. So the rank here, the maximum possible rank, would be m. Okay. Now, given that there is then a value of lambda such that the partial of L with respect to x, which is a function of the optimal x star, and lambda is less than or equal to 0, x star is greater than or equal to 0, and x star times Lx, so the partial of L with respect to x is equal to 0. So this is our complementary slackness condition. And we also require that the partial of L with respect to lambda, to each of the lambdas, is greater than or equal to 0. Lambda has to be greater than or equal to 0. And lambda times the partial of L with respect to lambda has to be 0 for each of the lambdas. All right, we will return to these things in the next lecture. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.